All right, so I'm sure you're all very confused at this point. Let's see. Let me just also make sure that I'm recording properly because the last lecture apparently, for some reason, was recording a blank screen except for me talking, so that wasn't too good. So yeah, that's why it didn't get uploaded. All right, so today will be the day of Montes, so to speak. And again, we're going to be working off of the Monte Carlo simulator. Also, I did some more research into why I couldn't run Altair in my, out of my computer, and that's because it requires something that can translate JSON. So you need to use something like Jupyter, or basically you need to use this. It's designed for a specific Python programming environment called Jupyter, or to be used online. So if you want to use this graphing environment, then you just want to use it in the textbook. It's meant to deal with like web-based technologies and that kind of stuff. So that's one limitation of it. But sufficient for what we're doing in this class. So that was Monty Hall. Now today we're going to be talking about the Monty Hall problem, which we'll get into, which is a very famous problem that we have in computer science because we can use the other Monty to the other Monty to solve it. Now this is this is West Europe, or parts of it, and there's actually a lot of little countries in Europe, micronations, right? You all know about Vatican City, hopefully at some point, right? This tiny little absolute monarchy that lives right in Rome, essentially. But there's also other micronations. For instance, the nation of Andorra right over here. This is actually interesting. It's ruled over co-princes, one of which is the current president of France. In other words, whoever's the president of France is a co-prince of Andorra, I believe. They're very interesting. The way these little nations come about are always very, very interesting. These are smaller than like Luxembourg and Liechtenstein. The other one, though, the one that we care about today is located right over here, Monaco. Assuming I can zoom in properly to it, right? And Monaco is another micronation, very, very small. It's a small city-state. See, this is the country, and it's known for Monte Carlo specifically, right? That's what it's Monaco's, or was it Monaco? I think it's Monaco is known for. Monaco? I don't know. Specifically, it's named. It's a famous gambling city, so a lot of casinos there. A lot of gambling stuff. And the idea here is that we're going to be using something called a Monte Carlo simulation, which is basically, if you don't know what the odds of a specific game are, then play the darn game and figure it out. And the reason that we're going to be doing this is that we deal with simulations a lot in computer science and outside of it. They have this thing, they have this, it says that Steve Jobs here supposedly spoke to his idol Seymour Cray, and he made Cray supercomputers big. And he said, I used a Cray supercomputer to help me design the latest Mac, and Cray said, that's great, I just bought a Mac so I could help simulate and do the designs for the latest Cray. So, but the idea here is that we want to do simulations to try to figure out what is it that we want. Now, we've already kind of tried some approximations before, but here we're going to try approximating pi again as kind of the introduction here. So now pi, right, is this irrational number, which means that it goes on to infinity, infinite number of digits. And as such, the question is, how do you calculate all those digits? And the answer is we got to use a formula to approximate it. Because there's no simple fraction that will, give it to us, so we always have to approximate it. Now, there was Now, early on, very way back, I did something called the Leibniz formula, which is this formula over here that says pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, where you just add 2 to the denominator and flip the sign of each term. And as this adds up, it gets more and more and more accurate. Python can now, of course, that's black magic to everybody, right? It's not exactly intuitive, right? Why does this approximate pi over 4? I don't know. I'm not a mathematician. I just play one in front of a class. And a Monte Carlo simulation says, we're just gonna play a game instead and figure out what pi is from a game. So suppose basically we have a dartboard. Right? Suppose we have a dartboard, which I'm going to draw a very imperfect circle. Right? That's my dartboard. But pretend I drew a perfect circle. Okay. You throw darts at the board randomly. Some are going to hit the board, and some of them are going to be completely off target. Right? Some are going to hit right here. Some not so much. Okay. So what we're going to do is that we want to look at the ratio of stuff that lands inside the circle, the number of hits on the dartboard versus the number of misses we get. So how does that give us a value for pi? Well, let's go ahead and what we're going to do is we're going to set something up. We're going to have ourselves a coordinate square, basically a 1 by 1 coordinate square. Right? -1 over here, +1 over here, 1. And let's see, so I think it says it. Yeah, circle centered at 0, 0 with the radius 1, right? So we've got this circle, this very badly drawn circle, like criminally badly drawn, okay? And then we've got this square that's created by this unit square. Then we've got this unit square. So we put a unit circle inside a unit square, right? Unit meaning size 1 over here, right? Unit square, every side of the square is 1, right? It's particular, it's it's an easy bit of geometry, right? And then we've got a circle inside that. So our dartboard is in the middle of this square, and basically we're going to make the rule that all of our darts, they're going to either hit inside they're all going to hit inside the unit square, okay? Now it can be inside the dartboard or outside the dartboard, but it's going to be inside the square, okay? And we can actually use a bit of geometry, a bit of basic geometry and distance formulas to figure out whether something's inside the circle or not. But basically what we're going to do is that we're going to generate random numbers, and that will be where we throw it. Now we know the area of the circle is going to be pi r squared, and the area of the unit circle, area of the unit circle is pi. Area of the units. Oh yeah. Yeah, so the area of this unit circle is pi r squared, which 1 squared is just pi, right? So the amount of area that this circle takes up is pi. Okay. And the area of our 2 by 2 square that contains the dartboard is 4, right? Technically, this is actually not a unit square, my bad. This is actually because, it's not unit, right? Because this is 1 length, this is 1 length, this is 1 length, this is 1 length. My bad there. So technically, this is a 2 by 2, right? So what we can do is that we can, if we get the ratio of the number of the numbers that landed in the square to what landed outside, we'll get pi. But let's go ahead and just animate this to begin with, right? We're going to do it with Turtle Graphics, so bit bit easier right over here. So first thing we're going to do before we start doing any kind of simulation is let's just simulate how do we throw darts at a dartboard, right? Then we'll move to there. Okay, so first thing I have to do is we are going to import turtle. Okay, and now what am I going to do? Also we'll need to import random because I'll be dealing with random numbers a lot in this exercise. Okay, so we're going to stick with the default shape, but let's say Bob is equal to Boib. Bob is equal to turtle to create a new turtle. I know I moved a bit fast, but right now all I'm concerned about is that I'm going to be creating random numbers to throw the turtle at. Throw the turtle at, sure. And so what I'm going to do is I'm going to generate a bunch of random numbers. For blank in range 1000, what I'm going to do is I'm going to throw the turtle at a bunch of spaces, a bunch of random spaces 1,000 times. The way I'm going to do this, bob.pen up. Okay, it's actually fairly straightforward. I generate the x I want to go to by saying random dot next. Let's see. Well, actually, I got to look up how random works again because I always forget. So random in Python. How does that work? Generate pseudo-random numbers. Zoom in so you guys aren't having to squint. Okay, lots of stuff there, but Alright, so integers. Rand int gives me a random integer, but I don't want an integer. I'd like a decimal point. It's got to be between 0. It's got to be a floating point number. So math dot so random dot seed, random dot get set state, jump ahead, random bits, random range. Okay, random dot shuffle, rample dot sample, random floating point between. Okay, here we go. That's what we want. Random dot random returns a random floating point between 0 and 1, but let's see if it does the work for me. Random.uniform returns a random floating point number n such that n is between a and b. So in other words, I can use this. Okay, so uniform, by the way, means that it's a uniform distribution here, meaning that all the numbers are equally likely, right? If I'm throwing darts randomly at this magic dartboard, it's going to be equally likely that it lands anywhere. So, random dot. Oh, I've already forgotten the name of it. Uniform. Random dot uniform. So random point from -1 to +1, and y coordinate is also going to be randomly from -1 to +1. Okay, and then I'm going to say, Bob, go to that spot. That's how I'm throwing you there. Bob.go to x, y. Okay, and then stamp yourself. And that's all I need, actually, for this, I think. Except that, basically, that it's all kind of just one nesty blob, I think, because it's just so. Yeah. Recommend myturtle.tracer for faster animation. Yeah. So let's call it. My turtle in this case is Bob. Bob. Save and run. Yeah, so it doesn't seem to be doing much because of course we are dealing with the fact that basically that it's hard to see those very, very tiny numbers in this location. So why don't we go ahead and multiply that by 100 just to make it visible. Right? So let's go ahead and multiply by 100 to make it visible. There we go. So as you can see, what's going on is that we're throwing darts and it's kind of outlining a square here, right? Not a circle, but actually what we said is that that the requirements are that it has to land in a square. Right? So actually let's just go ahead and get the point, and rather than setting x and y, we'll just transform it over here. That will make it easier. This isn't going to change it. I'm just changing where I multiply it by 100. If I change it to 200 here, and this is just simply so for visualization purposes. Right now, since it's a 200 by 200 space, that's a bit easier to see. And it's a lot. So we're just throwing a lot of darts at the dartboard over here. Okay. So the question is now, how do I show? You should also review window.setWorldCoordinates. That's right. That's the easier way to do it. So let's take a look at window.setWorldCoordinates because we really haven't experimented with that. So Turtle, not Turtle Dove, great author. One of his series that I really love is What If Aliens Invaded During the World War II? It's a very, very good series. Let's see. Set world coordinates basically says, the x-coordinate of the upper left, this sounds fantastic. So then, in this case, we won't need to change it at all. All right. Specifically, what we're going to do over here is that we are going to use this function, set world coordinates. Basically, we've got this. Yeah, it says error exceeded time limit for running. That's okay. We won't have to adjust this anymore. What we're going to do over here is use set world coordinates, which you should have seen kind of in passing in your problem, in your hurricane tracker. And what it does is it says, this box is kind of abstract. What would you like this coordinate to be? What would you like this coordinate to be? So if you just wanted it to be 100 by 100, you could say, if you just wanted to be 100 by 100, you could say, this one is a phone call in the middle of class. This one could be 0. This could be this could be, 0, 100, also, and this could be, let's see, what is it? Lower left x, lower left y, upper right x, upper right y. So it wants the xy of this location and the xy of this location. So since we're dealing with this unit circle, this is going to be -1, -1 to 1, 1, or not. So that's what we want. We want -1 for my lower left, -1 to 1 and 1, and now save and run. Bad syntax on line 6. What did I do? Did something terrible. What did I do that was terrible? Bad syntax. Module has no. Okay. So I have to do bob.setWorldCoordinates. Let's see. Turtle has no attribute. Okay, so I think what I have to do is, I was just going over there, but it's turtle screen, so I think I have to do, so I have to use window somewhere. Let's see. My bad. Are we in Turtles, Windows, Turtle State, Window Control? Yep, Turtle. WN is equal to turtle dot, and then turtle, I'm going to guess it's turtle screen. And then WN dot set word coordinates. Module has no attribute turtle screen. Screen? There we go. That's much better. Okay. So now the next step is we want to check if the distance, basically we want to set the color accordingly. So let's go ahead and say bob.color is blue. And basically we will want we will want anything that falls in the units. So we've drawn our square that the unit circles in. And now we want to say anything that's in our square is in the unit circle. That's actually not, sorry, anything that's within the unit circle should be colored so. That's not actually too hard to do. What we're, to figure out whether something's in the unit circle or not, right, what we do is we throw a dartboard. Now this thing is radius 1, right? That's what I mean by unit circle, radius 1, inside this 2x2 square. So we throw something in, and if it lands in here, all I have to do is ask, what's the distance to the center? If the distance to the center is 1 or less, then I'm inside the circle. Right? That's because that 1 is the radius. So if the distance to this to 0, 0 is 1 or less, boom, I'm good to go. If it's outside, that means it's the distance is going to be greater. Does that make sense? This is just annoying geometry, but that's all this is. So basically, we're saying it says over here that if the dart, since we know when a dart lands on the circle dartboard, if its distance is 0 to 0, 0 is less than or equal to 1.0, if its distance is less than or equal to 1. So this is the formula. We know this formula because the dartboard is 1. So what we can do is we can say, hey, distance is equal to math dot, I need to import math for the square root function. Import math. Math dot square root, which does exactly what you would think it does. X squared plus y squared, and that gives me the distance. And now it's fairly straightforward. If d is less than or equal to 1, Bob dot color red. So if the distance is such that it's inside the unit circle, great. Otherwise, color it blue. And now watch what happens. So we're throwing these darts at the dartboard, right? We're calculating the distance from the center, from 0. So we use this formula, right? 0 plus x plus 0 squared plus y plus 0 squared, and the square root of that gives us the Euclidean distance. Run this, and now the things inside the random points that are showing up inside this circle distance are turning red. Right? If I brought this up to 2,000, by the way, we'd get twice as many points. All right? Share this code with all the students. Okay, so you guys should be able to see it on your project page too now, if you need to. That looks pretty circular. So we're going to copy this down here in the next spot. Now that we have it, we can now say we now want to add counting and calculating what pi is. Okay. Let's see. So now that we have it, make a calculation pi. You can speed up the animation. Okay. So let's go with, let's draw this some more. So now let's go, we need more samples though, because 2,000 isn't enough to get an accurate sample. And we'll draw 100. Basically, we're going to skip, we're only going to show what's going to happen after we draw it 1,000 times after, and we'll pause for 25 milliseconds. This basically super speeds up the animation. That's pretty cool, isn't it? So what does turtle.tracer do? It basically helps with animation. What it does is says, I'm going to skip every 1,000 step. I'm going to skip everything but the 1,000th animation you do, and I'm going to draw everything else in the background, and then I'm going to draw it all at once. And then I'm going to pause for 25 seconds in between each. So we're going to, here with 1,000,000, it's going to pause each second as we draw. See, bam, and as you can see, every second it's giving me 1,000 new points. So because it doesn't have to draw, it's able, and says, I'm going to just draw it all at once, it doesn't really have much to do. So we can go even further on this. So now skip every 1,000, draw 25. Can we go up to 20,000? And eventually it's just going to just kind of center in on that. So now what we need to do is actually calculate pi. And what we want to do is just simply, all we need to do that is keep a count of the number of hits we got. Hits is equal to 0. These are the number of ones that landed inside of here. Hits plus equals 1. So now we're keeping track of the number of darts that landed inside this. And we know how many darts landed out we threw in total because we put that in. So now print hits. Let's do hits total is equal to, let's pull this out and put total in here. Hits total hits divided by total, which isn't going to give us pi. What that will give us is actually pi over 4. So 0.78 of them hit inside of this circle. But what we really need is it's going to be multiplied by 4, right? Because the area of our 2 by, so the ratio of the number of darts that hit the dartboard to the number of darts we throw would be pi over 2. Pi over 4, right? We've got a pi as our area. And our area of our circle is 4. So the ratio of the area of the areas is pi to 4. Okay? So if we multiply by 4, then we get pi. By total, rather 4 times hits divided by total. And now if we run this again, .14 is the ratio. 7.2. No, so it's not exactly inaccurate. We threw 20,000 of them, But again, like I was saying, so let's go and do 10,000 skips. This will run pretty quickly. And then we bring it up to 200,000. Let's see what happens. Might take a bit to run. A lot of the fluctuation in the color, by the way, is from the fact that basically our darts are shaped like arrows. Nope, and we ran out of time to run it. It prevents the page from generating an infinite loop. So. Let's see. So, what does it want? Then you want to repeat the simulation for several hundred or 1,000 times and keep the average of the predictions. So, right, if you want to get, aha. So now let's go ahead and take this, but we're going to do it without the drawing bit, because we really didn't need the drawing bit. Okay, to generate it, that was just graphics. Now that we know that it works and shown what it's doing, we're going to just delete the graphics bit of it. And what we're going to do here is actually do some calculations. So let's go ahead and do maybe 10. We'll do 1,000 of these. Bob Echo 2. Yep, we don't need Bob anymore. If D is less than 1, do that. And now it's going to run a lot faster, by the way. Instant, essentially. 3.14 there. But it's random, so we're going to be getting a lot of different values. Right? So here, they're approximating 3.14. Going up 1,000 or 2,000. Right. So let's go ahead and generate. Let's go ahead and try this. Trials is equal to lists, or sorry, let's go with results and trials. So we're going to basically graph. We're going to use the Altair that we've learned to basically graph the results we get. Let's do 2,000 experiments, each of length 2,000. Okay. How do I do that? Well, this is hitting this run button once is an experiment. So let's run this experiment 2,000 times and see all the values we get. So for experiment in range trials, total hits is equal to 0. Hits is equal to 0. If that goes up, hits is equal to 1. Okay, and then what we'll do over here is that we will results.append. Right, so we run through an experiment once, get a number of hits, and then we append 4 times hits divided by total number of throws for that experiment. And then we add that to the list, and then we'll print out our results and see what happens. Should run. Oh my, that might have been a bad idea. What? I see. Okay, now it's actively running. I know because my computer is kind of screaming at me, what have I done? Maybe 2,000 was a bit much for it to go with. Perhaps. Yeah, maybe. You just wanted data. All right, so yeah, it's a system timeout. So let's go ahead and do just 20 trials. There we go. Let's do maybe 100 trials. That should take 5 times as long. There we go. So these are the 100 results of our experiment right now. So let's go ahead and see like how random our data is, how random these experiments are by using Altair to graph it. I can remember how to use Altair. That was like a whole week ago. So we'll import Altair. We've got our results. That's what we need. So let's see. Chart is equal to altair.chart results. Is that how that works? Let's see. It'll let me know from an error. Okay. List object has no attribute values on line 26. So, second, let's go ahead and get it back to 20. Or let's just do 2 values right over here so that it goes quickly. So, this chapter. All right, let me just, again, check. Let me refresh myself on how to do this. Take your data first. That was it. So you take your data. Data is equal to altair.data. And then chart is equal to altair.chart. The data, if we run this, okay, it's exactly 1 argument 2 given. What are you on about? What line? On line 26. All right. Data is equal to trials results is equal to experiments is equal to results. I have to give it a name in Altair in the data for Altair. That's what I forgot. Okay, now we get no error. We chart that data, and then we say how do we want to do it. Mark is equal to Altair chart dot mark underscore bar, and then encode, and then we do encoding is equal to mark dot encode, and I'll just go ahead and copy this so that I don't have to keep flipping back and forth. Coding is equal to this, and we want the x-axis to be experiments, and y is and we don't need any that. Let's see. Oh, yep. Inc dot display to run it or to save it. Okay. Let's see. Let's go ahead and deal with 200 with 100 trials, or 20 trials because that will be quicker. Run it. Experiment results. Got that in there. Y is equal to value, not results. Okay, value. Let's see. Because we did this all last time, it was just a matter of me trying to remember what the heck I was doing. Right, so mark.data, mark bar, bar, mark.encode, x and y. Oh, right, I probably need to give it a guide as to what the data is. Ordinal. Okay, so Q. So why isn't it plotting it? Okay. Oh, right, the binning bit. That was what I... Let's see. That was it. That was it. That's what I've forgotten. What I need to declare what the y is. X is equal to experiments, and then y should be equal to y. Right, and this is all from last time. If you're lost, don't worry. I'm not going to make you graph too much. This is just more along the lines of what we can do with this. And there. We can see that got this weird looking kind of curve over here. That's only 20 results though, so let's go for 200 now and see what happens. So this is going to run for a bit, generate all those data. It does take a while to throw 200 times 2,000 darts. And what we get here is what we call a bell curve, which is basically saying that most of these results are ending up at somewhere at 3.14, right over here. And some of the outliers, not so much, which is pretty interesting. All right, so the next bit is actually a bit interesting over here. Let's see, what time is it, actually? I might want to just skip to them. I think it might be best to skip to the Monty Hall problem. And maybe I'll leave this for an exercise for you guys to do at some other point. So, let's talk about from Monte Carlo to Monty Hall. So, Monty Hall, as you saw at the beginning, is a game show. And the premise is, the Monty Hall problem, in terms of us, is fairly straightforward. Okay? Present you with 3 doors. The Monty Hall presents you with 3 doors over here. Doors 1, door 2, and door 3. Behind one of these doors lies a magnificent new car. Everybody wants a car. Magnificent new car. Doesn't really matter what it is, but it's a new car. And behind the other 2 doors are goats. Okay, now we're assuming here that the goat is much less desirable than that new car. Now, some people, like myself, wouldn't mind getting a new goat over a car, but I think we're in the minority here. So the problem assumes that behind one of these doors is a car, and the rest is something that you don't really care about. Okay? Something of great value and something that's not particularly valued. Okay? So we ask you, what do you want? Do you want door number 1, 2, or 3? Right? Doesn't really matter here. Let's assume that you say you want door number 2. So we'll go with this one, door number 2. Okay, doesn't really matter for the purpose of this exercise. Now here's the problem, or rather here is the, not like the issue, but like the problem description. Now that you've chosen your initial door, Monty Hall will ask to reveal one of the other doors, which he'll always open, for the sake of drama, it will always be another goat. Basically, he'll open up one of the 2 doors you didn't choose to reveal the goat that you didn't. Okay, we might open up door number 1 and say there's a goat there, or I might open up door number 3 and say, hey, look, there's a goat here. And now he presents you with a choice. Do you want to stay with your initial guess, or do you want to switch? Now, if you know the answer to this question, please don't reveal it. Right? Do you want to stay with your initial guess, or do you switch? So what's the chance? So the question is like, what's the chances? Initially, you might think that the chances are like on the face of it. It's like, well, one of these goats, right? One of these doors has a car. One of these doors has a coat, right? Because we're always going to throw out one of the doors that has it. We're always going to throw out a goat. Okay, before we present you with the choice to switch. Is it, it seems like a 50-50 chance, right? This either has a car or this one has a car, right? 50-50 if I stay or switch, so it doesn't matter. But it does very much strongly matter whether you stay or switch. It really does. Okay? And it's really, it's actually pretty complicated, but the idea here is that, actually it's not too complicated to describe this, if you just simply think through of all the possibilities, right? There's essentially just 3 of them. But this problem caused some controversy at some point, right? Monty Hall problem. You can check it up on Wikipedia. Monty Hall and Bossabon and the Media Furor, right? So it's a bit of a paradox, right? It was asked in Parade magazine like this: suppose you're on a game show, you're given the choice of 3 doors. 1 is a car, other 2 is a goat. You pick a door, say number 1. The host who knows behind what's the door opens the door, say number 3, which has a goat. He says to you, do you want to switch to number 2? Is it your advantage to switch? And then Vos Savant response was that the contestant should always switch, because using these assumptions that we've put in, that the host always reveals a goat, then contestants who switch have a 2/3 chance of winning the car over the goat. It's in your advantage always to switch. Where if you stick with your initial choice, it's only a 1/3 chance. And it's because of those initial probabilities. Now, I'll explain to you very easily why this is the case. But people were pissed, so to speak. Now, I'm not saying that it's because Vos Savant was a very smart woman who had a math column, specifically the woman part, but it was probably because she was a woman that, because this problem had been examined in other contexts by men and published in mathematics journals, but God forbid a woman throw in and suddenly you receive thousands of letters, including many from PhDs who all disagreed with her answer. So it was, now the reason this works is because you've got basically 3 assumptions, right? When we make our initial guess, there's 3 choices. There's 3 possibilities of what could happen. There's either a car behind this door, right? Or there's goat number 1, or goat number 2, right? Easiest if we keep them separate for this case, right? So if we initially choose car, now let's assume that we're always going to switch, okay? If we choose car as our initial guess, right? Monty's going to reveal either goat number 1 or goat number 2, right? Doesn't matter which one he reveals. And if we switch, we lose because we'll choose the other goat, okay? So if we choose the car and switch, initially, that's a loss for us. We don't know what we chose, but if we chose the car initially, we're going to lose if we switch. If we choose and we end up on goat 1, Monty's going to reveal goat number 2. And the other thing, by process of elimination, has to be a car. Right? If I choose goat 1, this would have to have goat 2. This is the one I'm getting rid of, so this has to have the car in it. So if I switch, I win. And goat number 2, similarly. If I choose goat number 2, goat number 1 gets revealed and is now out of the running. And so if I switch, I win. Get the car. So, it seems paradoxical, but when you think of it like as this is my strategy, and these are the possibilities when I switch, this works. And if I decide not to switch, the only time I win is when I initially choose the car, which I only had a 1/3 chance of doing, right? If there was, think about it this way, if there were 4 doors, 3 goats, 1 car, and we threw out 2 goats each time, and we revealed 2 goats, right? Your initial pick has only a quarter of landing correctly. But if you switch, now you've got 3/4, right? So so Paul Erdos, one of the most prolific mathematicians in history, so much so that that mathematicians actually have Erdos numbers, much like people have Bacon numbers. Bacon numbers. 6 degrees of separation to Kevin Bacon. Your Bacon number is basically how far of a performance you had from Kevin Bacon, who's a very prolific actor. So basically, if you've acted with Kevin Bacon, your Bacon number is 1. If you've acted with somebody who's acted with Kevin Bacon, your Bacon number is 2. And if you've acted with somebody with a Bacon number of 2, your Bacon number is 3, and so on and so forth. So it's just a small game. Erdos number is similar. If you've published with Paul Erdos, you've got an Erdos number of 1. If you've published with someone who published with Paul Erdos, you've got an Erdos number of 2, and so on and so forth. My Erdos number is 5 because I published with somebody who had an Erdos number of 4. Okay, and there is Bacon Erdos numbers, which is the lower of your Bacon number or your Erdos number for people who have acted and have had an Erdos number. So, but those people are rare. But anyway, the only way that he became convinced was a simulation demonstrating the result. And so if you're unconvinced, then perhaps we should simulate it. Right? So the idea here is that we can so let's go ahead and see. So the math behind is complicated, but what we can do is we can use a random number generator to put the prize behind the door. Okay? So what we'll do is that basically we'll create a list called doors over here. All right, we'll just simply do one iteration of this and then throw it into a loop. Okay? So here's our doors. Doors number 1, 2, and 3. We can use 1 to represent a car and 0 to represent a goat. So, and we'll need to use random. Okay? So initial setup for this is fairly straightforward. What we're going to do is that we're going to randomly choose one of these doors to hold the car. So random.next int 0 through 2 is equal to prize index, right? Basically, we're choosing the index. There we have 3 valid indices: door 0, door 1, door 2, because we're in the computer science version of this. And so we're saying choose a number between 0 and 2. Print prize index, right? Just to show that we are no attribute next int.
Boo. Randant. My bad. All right. Randant. 0. So see, as you can see, randant 0 to 2 works different than range. It goes up to and includes 2. So 0, 1, or 2. And it's going to give me an integer. So it's going to give me one of those. And so that one is going to be our prize. So doors, prize, index is equal to 1. And so now if I print out doors, we'll see we've got different configurations of doors over here, right? Everybody see how we've just created a bunch of different doors over here? We could simplify this a bit into one line, or rather than 2, but that would look pretty terrible. So we're going to choose a door. So now we've got, so basically we're going to be using this a whole lot. All right. Now we got 2 decisions here. We can either simulate with us always choosing the same door, or we can just randomly choose a door as our first one. I'm inclined to do that. So door choice is equal to again, we're going to choose one at random. Right? So right now this is our game. We're going to choose it at random. Print door choice. So here, right, chooses door 0. He'd lose, win, right? Because you choose, right? So what we can do, basically, we can figure out if it's a win or a loss fairly straightforward. If door choice, so if doors, let's actually make this a bit of an easier one. Doors. If doors choice equals 1, print winner. Else, we're going to delete this fairly soon, by the way. Loser. Right? So it seems like, and as expected, basically a third of the times we are getting loser. Let's go ahead and actually quantify that by repeating this experiment multiple times. Tab to indent it. For blank in range, the number of times you want to run the experiment, 100, or let's go with 1,000. Let's go ahead and do, actually let's do wins is equal to 0, games is equal to 1,000. So we simply say how many games we're going to play. And if you're a winner, let's stop printing this out. If we win, we're going to say wins plus equals 1. And that's it. And all we're going to do now is print print wins, games, wins divided by games. Syntax error, bad input on line 4. Forgot my colon. Okay. So basically that won 36% of the. So basically all of them just simply choosing. We're not even getting into the choices yet. We're just simply saying, I'm choosing a door. I'm choosing a door at random, and the prize is put into a random door. How many times am I getting it? Okay. So the next thing is now we need to simulate the. We're going to simulate how does this. We're going to simulate now what we do with the switching strategy. So now, what we got to do is that Monty has to reveal one of the he has to reveal a door that's not the that's not a car. So he's got to find a goat and basically expose it to us. Okay? Goat index is equal to, well, this is going to be a bit tricky. So we're going to choose a random dot rand int. This is going to be a bit tricky. I'm not going to be smart about this one. I'm just going to be very brute force about this. So initially what we're going to do is that Monty's going to look for his goat fairly straightforward. So he's going to choose one of the random indices, but while goat index is equal to the player's choice, right? We don't want to open up the player's door to show him what he's got, right? We want to choose something that he didn't choose. And then choose another one, right? Makes sense? Monty's gonna choose something, or choose a door to expose, right? But while that is equal to the door that I've currently chosen, I'm gonna choose another one. Or while doors dot prize index equals 1, or while I've chose, so again, I'm choosing one of these doors randomly. I got to choose one of them randomly open. My restrictions are I can't open the door with I can't reveal the door of the car, okay? And I can't reveal the door that the player's chosen, right? So I'm preventing that from happening. So, and while that's true, I'm just going to keep rechoosing it again until it happens. I'm not going to try to use any clever math or anything there. Okay, so now Monty's revealed his thing, and so let's go ahead and see what we can do here. I'm actually thinking of making this actually fairly simple, which is that I will say, okay, let's see. So we've got our door here, and now the question is, should I switch to Yeah, I'm just trying to think of the cleverest way to do, the most efficient way to do this, but let's just go through the logic basically straight away. So basically, basically I want to show what happens if I switch. Okay, if I switch, so basically now I got to switch my index. So choice is equal to, so it's going to be a couple cases. If choice equals 0, if goat index equal 1, choice equals 2, else choice equals 1. So basically, if I initially chose 0 and he revealed 1, then I choose 2 because I'm switching. 0 and 2 are the only ones left. Otherwise, it's only 0 and 1 left, so I'll choose 1. Elif, it's very important that this is an elif. Choice equals 1, and same logic over there. If goat index is equal to 0, then I choose 2. Otherwise, I'm going to choose 0. So, right, if I choose 1 and he's revealed 1, then if I've chosen 1 and he revealed index 0, then my only other choice is to pick index 2. If I chose 1 and he revealed index 2, then my only other choice is to pick index 0. And finally, what if I chose 3? What if I chose door number 2? If goat index is equal to 0, then my choice is limited to 1. Else, well, I'm on 2. He didn't choose 1. That meant he didn't choose 0. 0. That means that I need to switch to 0. Not goat index. Choice is equal to 0. So there. Then I've switched. And now, let's go ahead and run it to make sure I don't have any issues so far. Am I in an infinite loop here somehow? Web page is slowing you down. What would you like to do? I will wait. Did I have an infinite loop there? If goat.choice. Alright, so that seems to have worked. If goat.choice. Alright, so now print. So now all we have, let's go ahead and do our old statement. If door dot choice equals 1, print winner. And we'll also print out the doors. Print doors, comma, choice. Let's shrink this a bit so that you guys can see it. I don't know why this is taking so long to run. Oh, okay, so it says time limit exceeded on line 12. While goat index is equal to choice or doors. Okay, so I messed up somewhere in that while loop. Right, random gives me 0 to 2. So while goat index is equal to choice or oh. There we go. That's what was stopping. There we go. Now I hit it a lot. Right, my issue there was I'm using prize index, and so that was always true because the prize index is always 1. Goat index. So while the goat is equal to the choice or the goat index is not actually a goat, it's a car, we choose the goat index. So, so now what we're going to do is that if we are going to do wins plus equals 1. Okay, wins plus equal 1. And now we take all this over here, indent it, and we repeat it. For blank in range games, and now colon again. For range blank in range games. If I win, increase increase the total plus 1. Print wins compared to games compared to and let's go ahead and say so print wins games and wins divided by games. the fourth number over here is what the user's chosen. And we see that we now are winning 66% of the time by switching. And this is what a Monte Carlo simulation is. It's just literally playing the game and basically simulating it. If you're not sure of the statistics, if it's within your favor, simulate it and figure it out. And so here what we've done is that we've simulated this strategy of switching, and we're finding that basically we are getting a 66% chance of winning in this game. Right? It says to do it 10,000 times. Okay, we'll do it 10,000 times. So there you go. Questions about this one? So one of the most useful, so this is one of those really useful things you can do with computers, which is simulate stuff. So let's see, where are we going to go from here? So this is just simply the extension of what we've been talking about with data and that kind of stuff. Now, so does everybody understand the Monty Hall, or any questions about it? Right, so what we've done is that we generate our doors, we figure out where we're going to put the car, and then we have the user initially choose at random, and we put in the goat somewhere. The goat's got to go somewhere that the car isn't, and the door isn't. So the goat's got to go somewhere that the car isn't. We don't have to put the goat somewhere. We just simply need to reveal a goat. We need to reveal a goat, and the goat's got to get revealed where the user hasn't chosen that door, and we don't want to reveal the prize. So we're just simply opening a door that doesn't have the car or the user hasn't chosen. And then this block over here just simply is the logic for how to switch, right? If I chose door 0 and door 1 got revealed, then I have to switch to the other non-revealed door, which is 2. But if the other non-revealed door was 2, then I switch to 1. If I initially chose 1 and 0 got revealed, I switch to 2. Otherwise, I switch to 0. And that's just that logic. You only have 6 choices there because there's 6 combinations. And then if I match, great, I get +1. And we don't really need to simulate what would happen if you stayed still, because if you stayed still, that's the number of times you lose this game, which would be wins. So if you stayed still, it would be games minus wins over gains. So if you stay still, you only have a third of a chance of winning. All right, so for our next phase, we are not going to be using something in this textbook because the textbook doesn't really have the what I'm going to be going over next. Or this textbook does not have what we're going to be going over next. Which is specifically, we're going to be going over regular expressions. I want to do regular expressions as opposed to doing objects or going into dictionaries a bit more, because regular expressions are very useful, very, very, very useful if you heard me talk during the CS like 1000 seminar thing, where you will find the stuff on for our next lecture is on the alternate book that we have up here, Automate the Boring Stuff. So we're going to be going over chapter 7 in this book, which is also online, also free, and we're going to be talking about how to find regular expressions, or how to use regular expressions to find things.